Hi everyone, I am Santhi from Department of Mathematics and Statistics, Bhavan Vivekananda College. I am here with my lesson 24 in linear algebra on vector spaces. In this lesson, I am going to explain about kernel and range of a linear transformation. First, let us start with kernel of a linear transformation. It is even called as null space of a linear transformation. Earlier you learnt about null space of a matrix. So this kernel is also on par with the null space of a matrix, or you can here we'll say that null space of a linear transformation. Let us first look at the definition of kernel of a linear transformation. For this, let us take two vector spaces V and W. So definition goes like this. Let V and W be two vector spaces and T from V to W be a linear transformation. So T is from V to W, a linear transformation. That means if whenever X is there here, T of X will be there here. Then the kernel of T is a set of all the vectors in V such that T of U is equal to 0. That means kernel is a set of elements from V, the domain V, but they should satisfy some condition. What is that? T of U is equal to 0. That means the elements which are mapped to 0. See, when we define a linear transformation, suppose I have X here, T of X will be there. Suppose I have Y here, I may have T of Y here. There may be some other element which is suppose mapped to T of Z. But there are here, if I observe highlighted some elements here, that is these elements which are there in this set, where particularly if you take U. What is its image? T of U is equal to 0. That means U is mapped to 0. So let us suppose that all these elements which are there in this set with the color white color, this elements in this set, but they are all mapped to 0. Then this set we call it as kernel of linear transformation. That is, kernel T is defined as kernel T is equal to set containing U belong to V, the vector U from the domain such that T of U is equal to 0. Now we have some note points. First one, as we have seen in the diagram, kernel T is always a subset of V. And the second point, kernel T is also called as null space. Now let us prove a theorem on kernel. That is, let T from V to W be a linear transformation, then prove that kernel T is a subspace of V. So let us go for the proof. So it's given let T from V to W be a linear transformation and take the kernel. What is the kernel definition? Kernel T is equal to set containing U belong to V such that T of U is equal to 0. And as we mentioned before, this kernel will be a subset of V. So let us look here again about the diagram. So kernel is here for me, where all the elements in this kernel, suppose if U is there, this is mapped to 0 element. This is V, this is W, T is a mapping from here. All the elements in this kernel are mapped to 0 element. This is what we have. Now you have to prove that kernel T is a subspace of V. So for that, how do we prove? As I said, to be a subspace, we'll prove three conditions about. One is about 0 vector, another one is sum of any two vectors, then addition of vectors, that is, and the third one is a scalar multiplication. So let me take like that. First a 0 vector. Now since V is a vector space, there should be a 0 vector in V. Suppose that is 0. Then what is T of 0? T of 0 is 0. Under the mapping, T of 0 must show this 0 will be there in the kernel. Therefore, 0 belong to kernel T. First condition is satisfied. Now let us take the second condition. X comma Y belong to kernel T. So I am taking here, suppose this is X and this is Y. This is Y. Then if they are there in the kernel, what should be true? T of X is equal to 0 because X is mapped to 0. And T of Y is also equal to 0. Y is also mapped to 0. Now, you have to prove that now X plus Y is also there in the kernel. Now, since X and Y are there here, X plus Y Actually, it can be here in V. We have to prove that this x plus y is also there in the kernel. When will it be there in the kernel? When it is mapped to 0 element. So let us see what will be t of x plus y. So t of x plus y is equal to t of x plus t of y. Why it is? Since t is a linear transformation, in the definition we have t of x plus y is equal to t of x plus t of y. Then what is t of x? 0. What is t of y? 0. 0 plus 0, 0. So what did you prove now? X plus y, t of x plus y is also equal to 0. That means this x plus y is also mapped to 0 element. Then where should this x plus y to be? This x plus y must be there in U only because it is mapped to 0. So though you take x and y, two different elements in the kernel, their summation x plus y is also there in the kernel. Therefore x plus y belong to kernel T. Now let us go for the third one. That is regarding scalar multiplication. So let x belong to kernel T. So take an element x. Let me clear this and write. There can be so many points in this. So I'm taking, suppose x is there here. So obviously t of x will be 0. Then take c be any scalar. X belong to kernel T and c be any scalar. Then we have to prove that if you take say scalar c, where will cx be? Cx will be there in here v. You have to prove that this cx is also there here. It should come here. When will it be there in the kernel? When its t image is 0. If its image is 0, then it will come to the kernel. Let us look at its image. What is t of cx? Now, according to linear transformation, t of cx is equal to c into t of x. That is equal to c into t of x is 0. C into 0 is equal to 0. That means t of cx. T of cx is also equal to 0. So that is cx is also mapped to 0 means this cx will come to this cx also will be there in the kernel only. So you proved that cx also belongs to kernel T. So by these three conditions, by 1, 2 and 3, kernel T is a subspace of V. Now we will look at an example where we can describe kernel or find a basis or spanning set for kernel. So this is a procedure we will do either for describing a kernel or finding a basis or spanning set for kernel. So the example is like this, transformation T from P2 to R2 given by T of P is equal to P of 0, P of 1. It is given that it is a linear transformation. It is a linear transformation. And then find a polynomial P in P2, that is a domain, such that it spans kernel T, or you can say describe kernel of the linear transformation T. This is a problem given to us. So solution. So let us write what is a kernel definition. Kernel T is given by the definition which belong to the vector u in the domain V. If this is P and this is W and T is a linear transformation, u belong to V such that T of u is equal to 0. That means this u is mapped to 0 element. That is what kernel we mean by. So kernel T is set containing vector u in the vector space, the domain V, such that T of u is equal to 0. That is equal to. Now, what is our domain here? V is for us is P2 and the codomain is R2. So I will say it is U belong to P2 means how are the vectors in P2? Polynomial. So it is a polynomial P of T belong to P2. So vector U is nothing but polynomial P of T, and where the vector space with the domain is nothing but P2, the vector space of all polynomials of maximum degree 2, such that T of P of T is equal to 0. This is what we mean by. So this is equal to now what is P of T in P2? P of T will be equal to in the form of A plus BT plus CT square, that is in P2, such that now what is T of P of T defined as? This is T of P of T defined as P of 0, P of 1. It is a image is in R2, which has all column vectors of 2 rows. So such that what is T of P of T is nothing but P of 0, P of 1, that is equal to 0. What is 0 element in R2? It is 0, 0, which is equal to, it is such that A plus BT plus CT square, such that, now what do you mean by P of 0? In P of T, wherever T is there, substitute 0. So this will be A plus B into 0 plus C into 0 square, and P of 1 means A plus B into 1 plus C into 1 square. This is equal to 0, 0. So this will be equal to A plus BT plus CT square, such that here this is A and the second one is A plus B plus C is equal to 0, 0. So now we need to find this polynomial, that is you have to get the values of ABC. Now to find ABC, what is that we have with us here, which implies I will write A plus B plus C, the matrix is equal to 0, 0, implies A is equal to 0 and A plus B plus C is equal to 0. That implies if this is 1 and this is 2, and then 1 and 2 implies I can write B plus C is equal to 0, which implies B is equal to minus C. This is 3. So now what do I have? The polynomial, therefore what can I write here? Therefore P of T is equal to A plus BT plus CT square is nothing but A is 0 plus B is equal to minus C. So I will write it as minus C into T plus CT square, that is equal to CT square minus CT. So therefore kernel T is equal to, it is set containing polynomial P of T, that is equal to CT square minus CT, which I will write it as, it is set containing all polynomial which is in the form of, I can take common where C is common, T square minus T. So which has, it is equal to, C is any scalar here, so I can write it at it is a span of T square minus T. Therefore, this is a kernel. Kernel is span of T square minus T means all multiples of T square minus T, linear combinations of T square minus T will be the kernel of the transformation. And then what will be basis then? Basis for, why are we writing basis? We know that kernel T is a subspace of the domain. What is the domain? V means that is equal to P2. So kernel T is always a subspace, means it will have a basis. So what is basis of kernel T then? It is set containing T square minus T, and P is equal to T square minus T is the polynomial. This is answer. First they asked the question, polynomial that spans kernel T. This is what, how do procedure to find the to find the basis for kernel or to describe kernel of a linear transformation. Now we will define a range. What is range of a linear transformation? Let us look at its definition. Range of a linear transformation. Range is already you have been learning for functions. What is a range of a function? So that's range of a function is nothing but set of all the elements which have images of the elements of the domain. So that is the range. The same way it goes because of course linear transformation is also a mapping, is also a function. So let us look at its definition. Let V and W be two vector spaces like this I have taken here, and T from V to W be a linear transformation. Then the range of T is a set of all vectors T of X in W where X belong to V. All vectors T of X in W. So range vectors, where are range vectors? In the codomain W. But these vectors are nothing but images of vectors of V, because there may be some elements in W. Suppose there is an element here. But these are not mapped with elements in the domain. Only the elements which are there in this, these are only mapped, these are only there under the transformation. So all those vectors which are T of X in the form T of X in W, which are where X belong to V. So T of X means they should be T image of X. That is what range. So range T is equal to set containing T of X. So it has elements which are in the form of T of X. Where are they? They are in W such that X belong to V. Now let us note down some point about this. Range of T, already it is as it is shown in this diagram. Where is it? It is there in W. So it is always a subset of W. Now we learn a theorem on range. The same way how did we do theorem on the kernel. Now in the previous only we mentioned that range is a subset of the codomain. So here we know we'll prove that range is a subspace of the codomain. So for this the statement is let T from V to W be a linear transformation. Prove that a range of T is a subspace of W. So let us go through the proof. Let T from V to W be a linear transformation. Prove that range of T is a subspace of W. So then what is the range? Range T is equal to a set containing T of X belong to W such that X belong to V. This is already a subset of W. So first point, 0 belong to V and T of 0 is equal to 0 because 0 element will be mapped to 0 element only. So where will this T of 0 then, since it is T image, it will be there in the range of T because every T image will be in the range. So 0 element is there in the range. Then the second one, you should take two elements from the set whatever you are proving. You are proving range. So this is W, this is range. So take two elements T of X and T of Y from here in the range. Then when T of X, T of Y are there in the range, what does it mean? There is X in the domain. For T of Y, there is Y in the domain. So whenever T of X, T of Y belong to T implies X comma Y belong to V. Then what will be T of X plus T of Y? T is a linear transformation. We know that T of X plus T of Y is equal to T of X plus Y. Why? Since T is a linear transformation. So this is T of X plus Y. That means this X plus Y is some T image. T of X plus Y is a T image of X plus Y. So where will the T images be there? They belong to range T. Therefore T of X plus T of Y belong to range T. Why? Since X plus Y belong to V. That implies T of X plus T of Y belong to range of T. Now let us look at the third point. Take one element from the range. Let T of X belong to range of T. So the same way, this is a domain and this is codomain. This is range. I'll take here T of X and C be any scalar. Take any scalar C. So then what is C into T of X? Now this W is a vector space. What will we see into T of X? By linear transformation formula, C into T of X is T of Cx since T is a linear transformation. That means this T of Cx is here. T of Cx is here, it means it is some image of Cx. What does it mean? C into T of x will be there in the range of T. So you have proved the three conditions which are required for the subspace. By 1, 2 and 3, range T is a subspace of W. After the theorem, now let us go through describing range of a linear transformation. Or I can say it as finding a basis for range of a transformation T. So first I would like to give steps to be followed for the procedure. So take let T from V to W be a linear transformation. So I have here V and W and T is a linear transformation. Now the first step is consider a basis for the domain V. Particularly I will take standard basis. Sometimes it may be asked in the question to use another basis. If it is not asked anything, we will take it as standard basis and let it be B is equal to set containing B1, B2 and so on Bn. Where is this standard basis? It is in V. So in this the elements are B1, B2 and so on. So let me write it more clear here. Let me make it clear this. Yeah. So here if suppose I have like this, which is a standard basis, I will say this is a B. In this what are the elements I have? B1, B2 and so on. Right. Then let us see what is the second step. In the second step what you have to do is find, already you are given a transformation T and B1, B2 these are here. Find T of B1, T of B2 and so on T of Bn and let S is equal to set containing T of B1, T of B2 and so on T of Bn. So because here let us come to the diagram. You have T and you have B here. B1 is there, so T of B1 will be here. B2 is there, so you will have T of B2 and so on. If Bn is here, you will have even T of Bn. T of Bn. Like this you find whatever the basis elements are there, for each element find its image, T image. Then third step is if S is linearly independent, then S forms a basis for range of T. Because where is this S now for us? S is nothing but set containing these elements. This is S. So if this S form is linearly independent, then it forms a basis for the range. Fourth step, if S is not Li, then find a subset of S by deleting some vectors from S to get a basis. This procedure earlier we did in the before topics. When a spanning set is not linearly independent, you can be deleting the vectors to get a basis, to make it as Li and then basis to get a basis. And that is what the basis for the range of T, basis of range of T. This is a procedure to find out a basis for the range, or you can say describing range. Now let us work out a problem example on this. So let me take the example. let t from, this is the same example I am giving it, which we use it for the linear transformation and also finding the kernel, also the basis for the kernel. Linear transformation given by t of p is equal to p of 0, p of 1. The same thing last for kernel also I used. Then describe the range of t. So solution, let us go by steps. So here you are given t from p2 to r2 by t of p is equal to p of 0, p of 1. Now that is what we have here. This is p2 and this is r2. So what is the first step? We have to consider t is given a transformation from these two. So first step is consider what is the first step? Let us look here. Find, consider a basis for the domain V, that is especially standard basis. So what is the domain here? Domain is P2. What is the standard basis for P2? So I will consider the standard basis of P2, that is I will take B is equal to 1 t square. So I have here B 1 t square. This is B for me, standard basis. So what is the second step now? The second step is, after taking B is this basis, find t of B1, t of B2 and so on t of Bn. That means find the transformation images for the elements in the basis. So this is B1, B2, B3. Then what is t of B1? That is t of 1. So what is t of 1? How is the transformation given? T of p is nothing but p of 0, p of 1. So in whatever the polynomial t of 1, I will write it as first. I will write this one as a polynomial 1 in p2. This is a second degree polynomial. How do we write? 1 plus 0 into t plus 0 into t square. So I will write it as 1 plus 0 into t, 1 plus 0 into t plus 0 into t square, which is equal to, by mapping it is p of 0 means, let me say it is p of 0 first. Let me write this step and then, now what do I mean by p of 0? P of 0 means wherever t is there, put 0. It is 1 plus 0 into 0 plus 0 into 0 square. And what is p of 1? 1 plus 0, 0 into 1 plus 0 into 1 square. So this is nothing but 1, 1. So what is t of b1 for us? It is 1, 1. T of 1, so this 1 is mapped to 1, 1. 1 is mapped to, this is t of 1, 1, 1. Now let us see similarly what is t of b2. That is t of t. Now t, how do you write it as a t in p2? How do we write it? As a second degree polynomial. Constant is 0 plus 1 into t plus 0 into t square. Is it clear? So this is 0 plus 1 into t plus 0 into t square. So let me write this. Right. And then this will be equal to, what is it? By definition, this is equal to, again let me say it is p of 0, p of 1. That is equal to, what do you mean with p of 0? Wherever t is there, write 0. So 0 plus 1 into 0 plus 1 into 0 square. And p of 1 is wherever t is there, put 1. 0 plus 1 into 1 plus 0 into 1 square. Sorry, this is 0 into 0 square. So this will be equal to, so 0 and this is 1. So t of, what is the t of t now? T of b2 means t of t is 0, 1. So let me write here, this t of t is 0, 1. Now the third one, next one is t of b3. b3 is t square, t of t square. Now t square, how do I write it as a polynomial in P2? T square is 0 plus 0 into t plus 1 into t square, because there is no constant, so 0. There is no t term, so 0 into t plus t square term is there, 1 into t square. So this is t of 0 plus 0 into t plus 1 into t square. So let me clear this. So this will be equal to, again if I write p of 0 and p of 1, so this will be equal to, so 0 plus 0 into 0 plus 1 into 0 square, and then p of 1 means 0 plus 0 into 0 plus 1 into, so not 0, 0 here, 0 into 1 plus 1 into 1 square. So this will be equal to 0, and the next one is, this is t square, this is t square is 1 square, no? So this is 1 square, correct, 0, 1. So now I got this, next one is also, this t square is also mapped to 0, 1. So I don't need to write actually. I can say this is also mapped to 0, 1. So let us once again, if I draw the diagram again, see this is for us P2 and this is R2, and here I have the set 1 t, t square, and this is t is a transformation. This 1 is mapped to t of 1. What is t of 1? I got it as 1, 1, and t is mapped to 0, 1, and t square is also mapped to 0, 1. T of 1 is 1, 1, t of t is 0, 1, t of t square is also 0. Now what is our next step? The next step here in the problem you have is, whatever these you may just take them in a set S. If S is Li, then S forms a basis. So now we have to write this set S. So let S is equal to set containing t of b1, t of b2, t of b3, which is equal to t of b1 is 1, 1, t of b2 is 0, 1, and t of b3 is also 0, 1, so I don't need to write it. So it has only 2 elements. Now we have to check whether this is Li or not. So first, okay, let us do one thing. Let us take these 3 as 3 elements. Now clearly I will say S is not Li because, what is the reason? Because there are 2 repeated vectors. There are 0, 1 is repeated in this set. Now let us take S dash, a subset of this. So which vector I will delete? Repeated one. Usually if repeated is not there, then you will check whether they are Li or not, and then you will see whether which vector to be deleted. Here it is clearly, I can say 0, 1 is a multiple of 0, 1, linear combination, so I am deleting that. So I will take 1, 1 and 0, 1, and if this is Li, then I will say it forms a basis. So how to check it is Li or not? I will take det A is equal to, because I can easily simply do this. So it is equal to 1 minus 0, which is 1, not equal to 0. Therefore S dash is linearly independent. Hence S dash forms a basis for range of t. Range of t, or I can say range can be described as its span of these 2 vectors 1, 1, 0, 1. This is the way how do we describe range of a linear transformation, or we find a basis for linear transformation. Now let us look at the next example. Let M2 by 2 be the vector space of all 2 by 2 matrices. T from M2 by 2 to M2 by 2 is defined as T of A matrix A is equal to A plus A transpose, where A is equal to a 2 by 2 matrix A, B, C, D. Then you are asked some 1, 2, 3, 4 bits. Let us go one by one. First one is show that T is a linear transformation. So let us first work out the first one and then go for the next one. So solution. So you are given here A is equal to A, B, C, D. This belongs to M2 by 2. And uh, T from the vector space M2 by 2 to M2 by 2, it is given by, defined by, what is the condition it is given? T of A is equal to A plus A transpose. So first one we have to prove that T is a linear transformation. So let us come for this. What do we have to prove for linear transformation conditions? T of u plus v is equal to T of u plus T of v. And then second one, T of cu is equal to C into T of u, these two. So I will take the A bit. I have to take u and v, two elements from the domain. What is the domain for u? M2 by 2. This is a domain is M2 by 2. So even codomain is also M2 by 2. T is a transformation from these two. Let us take, let A comma B belong to M2 by 2. Then what then implies, can I say A plus B also belong to M2 by 2? Yes. Now what is T of A plus B? T of A plus B by definition, what is it given here? T of A is equal to A plus A transpose. So what is T of A plus B? A plus B plus A plus B transpose, that is equal to this. I can A plus B plus, and we have transpose properties. A plus B transpose is nothing but A transpose plus B transpose. I can write it as A plus A transpose plus B transpose, which is nothing but this is T of A plus this is T of B. So therefore T of A plus B is equal to T of A plus T of B for all A comma B belong to M2 by 2. And the second one, let C be a scalar and A belong to M2 by 2. Then which implies CA also will be there in M2 by 2. Why? Because if I take a matrix A, B, C, D and multiply with a scalar, I will get CA, CB, CC, CD, which is also there in M2 by 2. Multiplying by a scalar does not change the order. It will give the same matrix. So I can say here, if I take a scalar C and multiply it with the matrix A, it also belongs to M2 by 2. And what is T of CA by definition? It is CA plus CA transpose. This is nothing but I can say CA plus. Now this transpose is only for the matrix, not for any scalar. So I can bring out the scalar and I can write it as A transpose, which is equal to C into A plus A transpose, that implies which is equal to C into T of A, implies T of CA is equal to C into T of A for all A belong to M2 by 2 and scalar C. So therefore by A and B, T is a linear transformation. So the first one we have completed. What is that? The first one given asked in the question, that show that T is a linear transformation. This is done. Now the second one, describe kernel of T. So we'll go for describing kernel. So the second one, describing kernel. So let us write again what is kernel T. Kernel T is set containing U belong to the domain V such that T of U is equal to 0. This is the definition of the kernel. So this is equal to, so U belong to V. What is V? The domain V is M2 by 2 for us, and the range is also M2 by 2 codomain. So how are elements in the domain? Each one is a matrix. So U is nothing but for us a matrix A, that is in M2 by 2. So I'll take A belong to M2 by 2 such that T of A is equal to 0. Now in M2 by 2, how is any matrix in M2 by 2? A second order matrix A, B, C, D such that T of A is 0 means what is T of A? A plus A transpose is equal to 0. That is equal to a matrix A, B, C, D such that, now what is A? It is such that, let me say, A, B, C, D plus transpose of A, B, C, D is A, B, C, D is equal to 0, 0, 0, 0. That is equal to, so we have it has set containing, add these two matrices A plus A to A and B plus C, B plus C 2D is equal to 0, 0, 0, 0, where A, B, C, D are real numbers. So now we need to find these A, B, C, D values. Then you will get the kernel. So which implies I can say 2A is equal to 0, which implies A is equal to 0. Then B plus C is equal to 0. Then B plus C is also equal to 0. Again the same, B plus C 0 and B plus C 0. Two equations are the same. And then 2D is equal to 0 implies D is equal to 0. So now I have these three equations. A0, B plus C is 0. Now B plus C is 0 means I can write B is equal to minus C. So I have A is 0, B is minus C and D is 0. Therefore, kernel of transformation T is a matrix A, B, C, D that is equal to A is equal to 0, B is equal to minus C, C is equal to C, D is equal to 0. So this I can say, you can observe here, the four parameters in the matrix are only one parameter. I will write it as 0, minus 1, 1, 0. Which is equal to span of 0, minus 1, 1, 0. Therefore, basis for kernel T is equal to set containing 0, minus 1, 1, 0. That is the basis for the kernel. So now, what is our next task? The third point. Let us go through once and read the third point. Third point is, let B be any element in M2 by 2 such that B transpose is equal to B. Then find A in M2 by 2 such that T of A is equal to B. So let us write this again, the third one. Third one. So we are given let B be any matrix in B be any element. So let B belong to M2 by 2 such that B transpose is equal to B. Then find A in M2 by 2 again, because domain and codomain are the same, such that T of A is equal to B. So what do we mean by this? So let us just go through. This is domain M2 by 2. Even codomain is also M2 by 2. Both are the same here. And the T is a transformation. Now, B belong to M2 by 2 such that there is a matrix B here, which is satisfying the condition B transpose is equal to B. Now you have to find for this B, you have to get one A here. Now what do we have? Whenever A is there, this A is mapped to, what is the transformation? It is mapped to A plus A transpose, because we have every A, whenever T of A is equal to A plus A transpose, this is our transformation, linear transformation. We proved that it is a linear transformation. Now we are having a matrix B in the codomain such that B transpose is B. Now you have to get a pre-image A in the domain. But so what do you have to find now? This B which is satisfying B transpose is equal to B, and we have to get some coordination for this. So let me start with A for this. Let A is equal to A, B, C, D and T of A is equal to B. So I am taking, suppose T of A is equal to B. That implies I have A plus A transpose is equal to B. So I am coming in this way. I am first taking A here, and then I am supposing that this is B. B is now for me T of A. This B is equal to T of A. Now A plus A transpose is equal to B implies that is A, B, C, D plus A, B, C, D is equal to B. That is, what is this matrix? It is nothing but 2A, B plus C, 2D is equal to B. But here we can observe D 2A, B plus C, 2D transpose it. This will be also 2A, B plus C, 2D. That is, we have B transpose is equal to B for T of A is equal to B. So therefore, whatever B such that T of A is B is satisfying the condition that B transpose is equal to B. So what do you mean by that? That is, every A in M2 by 2 satisfies T of A is equal to B where B transpose is B. That is what we have done for whatever the B. So B transpose is equal to B. There is a matrix A, B, C, D in M2 by 2. This is what the third one. Now let us see, look at the fourth one. What is the fourth one? Fourth one, it is asked that, let us look at the fourth one. Fourth one, show that range T is the set of B with the property B of T is equal to B. So here we have to show that range of T has the elements in B belong to M2 by 2 such that B transpose is B. This is what we have to prove. Now in 3, what did we prove? In 3, we proved that for B in codomain M2 by 2 with B transpose is equal to B, there exists, let me write here, there exists A in M2 by 2, that is domain. So for every B there exists A in codomain, in the codomain. What do you mean by that? So entire this one, whatever the range of T is nothing but satisfying the same condition. What do you mean by that? The question is asked here that the range of T is the set B with verify with static property that B transpose is equal to B. Hence, we proved that range of T has all B such that B transpose is equal to B. This is what we have done in this problem. Actually, finding a range we can try doing by the other method, in the, whatever I was explained in the previous example. If you find in that way also, you will be getting the same thing.